Hello students, welcome to class 11 physics class. In last class we discussed about the cyclic process, the work done in cyclic process and some two numericals. Okay. Now in this class we discuss about the first law of thermodynamics, or you can say that from here the thermodynamics main topic started. So what is the statement of first law of thermodynamics? First law of thermodynamics is nothing but it is a law of conservation of energy. Okay, so according to the first law of thermodynamics, it states that if we supply some heat to any system, whatever system you have, and the system has one condition that it is capable of doing work, it is a condition or it is a characteristics of that system. Where we supply the heat, the system is capable of doing work. Then what amount of heat you supplied, some amount of heat is absorbed by the system, it will be equal to the not some, the quantity of heat absorbed by the system will be equal to the sum of the increase in internal energy and the external work done by the system on the surroundings. Whatever the amount you supply to the system, that in a quantity of heat it absorbed by the system, that is equal to the sum part of that heat its increase its internal energy means kinetic energy, molecular kinetic energy plus molecular potential energy, and the sum part doing external work by the system on the surroundings, okay. Mathematical expression of this first law of thermodynamics, delta Q equals to del U plus del W. Delta means change. Any change if happening in the system, it can be written as delta. So delta Q, that heat supply to the system, so that heat also be changes. Sometimes we supply more amount of heat, sometimes we supply less amount of heat. That means it is not constant. Heat also, whatever the amount of heat we supply to the system, it also be changes. That's why we use delta Q. In some books it will be written as dq, that little bit amount of heat it will be supplied, that's why they will consider as a dq. Delta W, work done by the system on the surroundings. This work done also be changes, sometimes more, sometimes less. And increase in internal energy. There is a change in internal energy, increase, always increase. That's why delta U. Delta U represent change in internal energy of the system. So mathematically we can write delta Q, the heat supply to the system, equals to delta U, increase in or change in internal energy, plus delta W, work done by the system on the surroundings. This is the first law of thermodynamics. Now it is another form. In place of delta W we can write that work done also be, we can write in terms of pressure and volume. How? In this figure you see that we take one container which contains some gas with movable piston. Now the gas does the work in moving piston. You see that the gas will does the work in moving piston. So it will move a little bit distance, that is dx, the work done by the system against the constant pressure P. P, because gas work done by the gas, that is in a upward direction, but the constant pressure direction is opposite to the gas pressure. So whatever the work done by the system, that is always against the constant pressure P. So that is equals to delta W equals to, because work done also be changes, that delta W equals to force into displacement. So force means pressure into area. Area of the cross section is A, So P into A into dx, and A into dx gives us the change in volume. Change in volume. P delta V. P delta V. In place of dx, you can also write delta x. Okay. But here, because it is small, so A into dx, A dx gives us the change in volume, that is delta V. Or sometimes in some books it will written as PdV. So anything you can write, whatever you write, you just mention over there. So delta W equals to P into delta V. So in this equation, in place of W, we can write delta Q equals to del U plus P into delta V. This is the another form of first law of thermodynamics. Clear? Okay. Now, too many very important things we discuss. That is a specific heat of gas. We know that we also studied, I think, in class 9. I don't remember, whatever. Constant molar specific heat at constant volume and constant pressure. Little bit idea we have. So here we get details about it. Specific heats of a gas. What happens when the gases are heated? When the gases are heated, there will be change in temperature. That change is very small. Small change in temperature. It causes a considerable change for volume as well as the pressure. Whenever gas is heated, small change in temperature change is very small. Gas will be heated. So if you measure the temperature by the using the thermometer, temperature change is very less. But within that small change in temperature, you see that the volume and pressure is change a considerable change. Very worst change of volume and the pressure. So due to which the specific heat of gas can have any value between 0 to infinity because of this relation. For small change in temperature causes a considerable change of volume and pressure. Therefore, to fix the values of specific heat of a gas, either the volume or pressure is kept constant. That's why when any one will be constant, then we define the other one. That's in depending upon this, we have two types of molar specific heat of gas. One, molar specific heat of gas at constant volume, or it is known as Cv, denoted by C suffix V. So how we define it? The quantity of heat required to raise the temperature of 1 mole of gas through 1 K or 1 degree Celsius when the volume is kept constant is called molar specific heat. At constant volume, whatever the amount of quantity of heat we require to raise the temperature of 1 degree or 1 Kelvin, that is called specific heat, molar specific heat at constant volume. It is denoted by Cv and its SI unit is joule per Kelvin per mole. Joule, Kelvin inverse, mole inverse. Okay. Molar specific heat of gas at constant pressure. It is first one is under the constant volume. This is under the constant pressure. If pressure is constant, then the quantity of heat is required to raise the temperature by 1 Kelvin or 1 degree is called molar specific heat at constant pressure. Okay, under the pressure constant, you need the amount of quantity required the temperature of 1 degree Celsius or 1 Kelvin, that is called molar specific heat of gas at constant pressure. And if volume is constant, same thing, the quantity of heat you need to raise the temperature 1 Kelvin or 1 degree Celsius, that is called molar specific heat of gas at constant volume. So constant pressure, it is denoted by Cp and its SI unit also be same, joule per Kelvin per mole or joule Kelvin inverse mole inverse. These are the two types of molar specific heat of gas. Clear? Okay. Now, in between these two molar specific heat of gas, we see that, or we have some value of Cp and Cv. After the examination or experiment, we conclude Cp always greater than Cv. Cp always greater than Cv. But why? That will explain here. So what happens if the gas is heated under constant volume? Whenever the gas is heated at constant volume is constant, okay? That means there is no expansion of gas. If no expansion, then no external work is there. External work delta W is 0. You supply the heat from outside of that system, then this total heat is converted to increase in internal energy. No work done is there because volume is constant. No expansion is there. If no expansion is there, work done is 0. So if we consider, or if we use the first law of thermodynamics, delta Q equals to del U plus del W, in that place of del W we can write 0 because no work done is there. So delta Q equals to delta U. So whatever the amount of heat we supply to the system, the total amount of heat is converted to increase in internal energy of the gas. But so only one thing is done by that supply heat. Only one case is there. But under the constant pressure, when the gas is heated, that gas is used for two purposes. One, increase in internal energy. Another one part is doing the external work, because whenever the gas is heated, it will expand. Under the constant pressure, it will expand. That means the some part of the supply heat increase the internal energy of the gas, and some part it is used for doing external work. So under Cv we get only one thing, that is only the increase in kinetic energy, but under the constant pressure we get two things. As a product we get two things: one, increase in internal energy, plus external work done. Because in Cp we get more two outputs, and in Cv we get only one output. So if output is increased, that means that process is very good and that process is more than the another one. That's why Cp is greater than Cv, because under the constant pressure, the whatever the heat is supplied to the system, it is used for two purposes, but in Cv it is used only for one purpose, that is increase in internal energy. I hope you understand why Cp is greater than Cv. So in both cases, constant volume and constant pressure, the increase in internal energy is same as the rise in temperature is the same for the same of the gases. Therefore, heat supplied at constant pressure is more than heat supplied at constant volume by an amount of heat which is used for doing external work. Because in constant pressure we get one extra output, that is external work done. So the supplied heat is more than the constant volume. So this explains why specific heat of gas at constant pressure is greater than the specific heat of gas under constant volume. Cp always greater than Cv. And there is a one relation between Cp and Cv that is discovered by scientist Mayers. So that relation is called Mayer's relation, and that is Cp minus Cv equals to R. R is called universal gas constant, and it is always positive. It is always positive. So Cp greater than Cv. We proved this Mayer's formula. It is included in your syllabus. Mayer's formula derivation, Cp minus Cv equals to R. Okay. So in first law of thermodynamics, in place of delta, I will write as a d. Okay, small change. dq equals to du plus p dv. In place of work done, we write pressure into dv. Now at constant volume, that is Cv, Cv equals to dq by dt at under constant volume. That's why we write a suffix at V. So dq, because at constant volume no work done is there, no change in volume, so that second term, that p dv, that term will be 0. So we have only du by dt at constant volume. This is equation number 1. But at constant pressure, Cp equals to dq by dt at constant pressure, that is equals to du by dt of p plus p constant pressure dv by dt. Both two output we have at constant pressure. This is equation number 2. Now from equation 1 and equation 2, the first part, that du by dt suffix v and suffix p, okay, we dropped because the increase in internal energy depends only on the T, capital T temperature, not the volume and the pressure. Just only depends on the temperature, increase in internal energy. That's why we can write the equation like this way. Cv equals to du by dt without any suffix, and Cp equals to du by dt without any suffix, but the second term part p into dv by dt, it is with the suffix part p at constant pressure, p dv by dt at suffix p. Just first part we removed. Now Cp minus Cv equals to that, then these two parts will cancel each other, so we have only p into dv by dt of p. That is equation number 3. Okay, so we have to find out this value p into dv by dt under constant pressure. So we use the ideal gas equation. For 1 mole of an ideal gas equation, we know that pv equals to RT. If n mole of gas is there, then we can write pv equals to nRT. So here I consider 1 mole of gas, that's why n equals to 1. So pv equals to R into T. Now we differentiate both sides with respect to T for under the constant pressure, because in third equation we have to find out dv by dt under constant pressure. That's why we differentiate with respect to T for constant pressure. So what we can write, p dv by dt at suffix p, that is equals to R into dt by dt plus T into dr by dt. But R is a constant, so change in the constant does not change, so that term will be 0. So we have only the first term, dt cancel, we have R. And in this part, p dv by dt plus another one term also we can write v into dp by dt. But dp by dt pressure is constant, pressure is not changed with the temperature, so that part also be 0. That's why I will write only one part, p into dv by dt at constant pressure, that is equals to R. Now we put this value in equation 3, so we have Cp minus Cv equals to R. Cp minus Cv equals to R, and this is the Mayer's formula. This is discovered by scientist Mayer's. That's why this formula is known as Mayer's formula. Now here two conclusion will also be there. If Cp and Cv is used for work done of the system, either it will be by the system or on the system, but if it is in unit of work done, then we can use only Cp minus Cv equals to R. But whenever Cp and Cv are units of heat, joule, calorie, okay, so we use this formula R by J. J means joule. Cp minus Cv, that is equals to R by J. Whenever Cp and Cv are the units of heat. If it will be units of work done, then it's only simple formula Cp minus Cv equals to R. R is called universal gas constant. Clear? Okay, so if you have any doubt, any step, if you have any problem, please write in a comment box. And please you do one thing, each step you write in your copy and do it by own. If any problem in any place, any problem you arise, please inform me in a comment, write me in comment box, you write this part or this line you did not understand, so I will make that video again for you only. Okay, Thank you very much. Have a nice day. Bye bye.